In this video, we see a paper titled Multiway Spectral Graph Partitioning, written by Professor Lars Elden. To be noted, this paper is very beautifully written, and let us go through this paper. This paper is about how an undirected graph can be partitioned into k. K can be greater than 2 using a standardized spectral method. The crux of spectral method for k greater than 2 or k maybe 2 partitioning of undirected graph is using eigenvalues of the normalized adjacent matrix, which we will be seeing in a forthcoming in a later part of this paper. So the crux of the paper is that there is a well established relations between eigenvalues of the normalized adjacent matrix or normalized graph Laplacian, and the way to partition the graph undirected graph into k greater than equal to 2 is here well established. Let us go through this paper. So let us consider G to be an undirected graph of having n nodes. The key problem here is to partition this given undirected graph into k subgraphs, such a way that the partition k subgraphs are well internally connected, and also this subcomponent of the subcomponent, that is this subgraph, is loosely connected to the other partition graphs. We all know that the spectral to partitioning, based on the work done by Fiedler, is well established mathematical theory. So here we extend this well established theory to the spectral k partitioning, and k is greater than 2. So let us go to consider these kind of details. Let us first define what is meant by a cost function or cut function for partitioning this graph into subgraphs. So we define a certain cost function. The objective is to minimize this cost function so that it is formulated as an optimization NP hard problem. So because of this NP hardness, we try to make some relaxing technology, and we try to formulate this minimization problem over a n-dimensional vector space, and we try to identify k smallest eigenvalues of the Laplacian of the graph. So such a way that once the eigenvalue problem is solved, we can identify uh, n cross k eigenvectors, and in this n cross k eigenvectors, each row is formulated as a data point, and then once these eigenvectors are formulated in a k dimensional space, then each row of the eigenvectors can be as a point. Then we can use a standardized clustering methods to partition this the cluster these endpoints. So this is the standardized formulations. So here the objective would be to identify the eigenvector matrix of first k largest eigenvalues. So on this formulated problem have two observations. One is the informations for case partitioning is contained not on the eigenvectors, like not on the k eigenvectors, but the subspace formulated by the k eigenvectors. So the second idea would be here to formulate a matrix called n cross k, where each row has only one non-zero values to the particular kth column. That kth column will belonging to the particular partitioning. So Sij will be non-zero only on one particular value, and other ij values will become 0. So this can be formulated as a minimization problem like 1.2, which will come later part of the sections. So here we consider the paper is organized into different sections. The section 2 will give you some overall view about what are the different properties of the matrix and their notations, and section 3 will be giving you about the classical two partitioning algorithms, and section 4 will introduce about this novel technology of k partitioning problem, extending the section 3 of classical to partitioning problems. And section 5 will be giving about certain numerical examples, and section C will give some final conclusions. So we will be not going deep into the how the numerical examples are executed, but this paper is mainly focused upon how this classical to partitioning problem is defined, how that classical to partitioning problem can be extended to k greater than 2. So the notations are very standardized. That indicator form, matrix indicator form is something like expressed in this way. Like for a permutation matrix, this can be a diagonalizable, and also there can be if there is an integers from 1 to n, and that can be grouping into k disjoint non-empty sets. And symmetric, these are some of the eigenvectors, and we know that the norm of the matrix can be a standardized Frobenius norm. And we consider let B be an unnormalized adjacency matrix, and let D be a vector called degree vector. It means that the ith element of the degree is the number of edges of the node I that is being connected with the other nodes of the graph. Then the normalized adjacency matrix can be defined by these formulations, and the normalized adjacency matrix have eigenvalues from lambda I 1 to n in such a way that the ordering can be lambda 1 greater than lambda 2 to lambda n. And normalized Laplacian matrix can be defined by I minus a, and eigenvalues are here. The one important factor is the normalized adjacency matrix and normalized Laplacian matrix are well connected through the eigenvalue problem. The reason is their eigenvalues are equivalent and their eigenvectors are the same. And we know that a subgraph is a subset of nodes and their corresponding edges. So the connectedness of the graph is something related to the irreducibility property of the adjacency matrix. Any symmetric matrix is reducible if there exists a permutation matrix P such that, uh, for example, a matrix A, PA, P transpose can be diagonalizable, something similar to like that, block diagonalizable. So this is if we cannot able to find out a permutation matrix where it cannot be diagonalizable, then it is called as irreducible matrix. So if those undirected graphs are well connected, then it means that the adjacency matrix is irreducible. So if it is a k reducible, then it has to be a k diagonalizable formulations. So another important factor is that normalized adjacency matrix has the largest eigenvalue is equal to 1, and their eigenvector is defined as this equations, and x1 is called as a Perron vector, and lambda 1 is the largest eigenvalue, and it will be a very simple eigenvalue. And the second eigenvalue is strictly should be less than 1, because lambda 1 is the largest eigenvalue, and due to orthogonality, and this first eigenvector and second eigenvector should become are both orthogonal, so that their inner product is 0. So the x2 is called as a Fiedler vector and x1 is called as a Perron vector. So now we come to the classical spectral to K partitioning. The idea behind is to minimize the cost of splitting the graph into two as small as possible. The cut function or the cost function to be minimized is defined as a conductance, and the equation is defined here. And the numerator is something like sum of all the weights of all the edges uh, uh, that is connecting the one subgraph to the another subgraph, so that that minimize that the connectedness between the two graph is minimized, and also the denominator is such a way that it has a reasonable number of edges in the each subgraph. So that is what it termed as a volume of R and the volume of the RC. And the Chigger constant is something like the min and this is the cost function. The minimized cost function is termed to be as a hg, And there is an important property that the hg will be less than 1 minus lambda 2. It means that the lambda 2 should be close to lambda 1. That means it close to 1 as much as possible. That is not only that is been requirement, and another requirement should be the eigenvector 1 should be greater than, it should be a parent vector. The eigenvector 2 should be orthogonal to the eigenvector 1, that is the Fiedler vector. And the algorithm is given in the 3.1. So the another important property is the ones, if it is a diagonalizable, and the normalized adjacent matrix can be written as something like this, and the corresponding eigenvectors is non-unique, can be written something like this. But if we establish a small connection between these two one, then the eigenvector matrix can be defined as something like this. If you see from this xe and x, their eigenvectors are only being not changed drastically, they are changed only by an epsilon value, and their eigenvector space is only rotated to a 45-degree, and their values are not changed that drastically, and they are changed only by an epsilon value. So this is the crux of the problem. This idea can be generalized for the k greater than 2. So the idea would be to compute the two largest eigenvalues of the normalized adjacent matrix, which we defined earlier in the matrix A, and then to try to compute the eigenvectors x1 and x2. The x1 and x2 will be closely to the Perron and Fiedler vector. And once we know that x2 is a Fiedler vector, then that they have minus and positive values, because x1 should be orthogonal to x2, and x2, this minus and negative value will be ascending from smallest to largest value. Then there will be negative and positive values. Then we will try to find out around the neighborhood of the change of values, try to find out which element has to be disconnected. So choose that element and try to reorder and try to split again until this conductance that we have defined here becoming a smaller value. So this algorithm 3.1 can be extended straight away to 3.2, sorry, to k greater than 2. And one of the idea we can use directly the idea of 3.1 to use recursively, like the split the first split it into two, then take the first one, then again split it into two, take the second one, again split it. So those that can be easily straightforwardly extended. But one of the thing is we will be missing out certain kind of implicit informations contained in the parent graphs. So it would be better to directly make a k greater than or equal to two partitions. For example, k can be 5 or 6 or 7, to directly doing rather than to do it recursively, so that the informations originally contained in the parent graph won't be lost. So the idea, another one thing is another second way to extend to directly computing the k largest part k greater than to partitioning will be to first identify the k largest eigenvalues and the corresponding eigenvectors and formulate an eigenvector matrix, and each row can be considered a point in a k-dimensional space, and use the standardized method of k-means algorithm. This again has the negative advantage would be to that k-means algorithm is the way how we implemented is very sensitive, and in different way of implementations will give you a different kind of partitioning, and it won't be an invariance, it doesn't carry forward the invariance properties. So this is a second algorithm. This also has some second error. So the third possibility is the one what we are going to define now. So we try to formulate a normalized adjacency matrix and their corresponding eigenvalues, and we define that eigenvalues are ordered in such a way that lambda k is greater than or equal to lambda k plus 1, and we try to find out a minimization problem that in 4.2. It means that that is being solved by an eigenvector matrix x of the normalized adjacent matrix, and similar to 1 minus lambda to we define it in k equal to 2. We define by lk, it's called as some kind of the properties that we wanted to minimize that implicitly contained for the k partitioning. this information here, it shows that in order to have this lk to be close 0, that lambda v, that v is equal to 2 to k should be close to 1. It means that it will be close to the largest eigenvalue, that lambda is equal to 1. So they have established certain mathematical theory such a way that these are the ordering happening. And so there are some mathematical theory established which we as algorithmic point of view just try to right, you just read it, it will be a well and understandable part, but I am just skimming through this part for the reason to be make the video within 15 minutes. Here what the crux of this part is something like a very simple enough. So here what they do is this is an agency matrix, and the agency matrix can be maybe it can be make into a partition into two these parts. And this part, if it is an reducible one, this part should be as much zero as possible, and it should have the higher weightage. So then we try to formulate cut functions. The cut functions can be formulated something like this, and we make a matrix of this cut matrix. And once that is being formulated, then we try to formulate a symmetric matrix similar to using these informations here. And once the norm of this symmetric matrix is shown to be as a cut value or something, and this value will give you that how much it can be a partition, the graph, graph can be partitions, that this cut function is been will be less than or equal to this value at where we define is equal to 1 minus lambda 2 for k is equal to 2. So this is the established theory, and for that, those theories are being given above, which is not that much related to the algorithmic point of view. Now we define the algorithmic point of view. For that, what we needed is, as mentioned earlier, we try to find out the eigenvectors. But eigenvectors for the not if it is not in an indicator form, we try to find out some rotation matrix so that it becomes an indicator form. And once that is we try to find out, that indicator form is defined as this matrix. But in the given eigenvector, if it's not indicator form, we try to find a rotation matrix so that the norm of this expected indicator form and this combined one as close as possible. So we try to make an iteratively, we try, it's kind of an iterative algorithm. So what this is an algorithm for the k partitioning algorithm. So we try to find out the eigenmatrix x and the corresponding largest eigenvalues of a. And once we try to find out the q matrix for which we can formulate this indicator form, then with the indicator form matrix is formulated using the algorithm 4.2, which is the contribution from this paper. Then we can find out the cut functions as defined as in the algorithm 3.1. So here the 4.2 is something like an iterative part. We try to guess an indicator matrix. That indicator matrix, once we guess the indicator matrix, we try to make a singular value decomposition of this, and then we try to identify the q. Once we identify the q, then we try to identify the indicator form, like let us call this as y. Then until we make certain convergence, the convergence would be something like this, minimizing this norm. Once this been integrated with this part, this algorithm will be similar to the algorithm of 3.1, like finding a parent vector and a fiddler vector and trying to rearrange the things and try to identify the sign of change and trying to make a partitioning. So similar to that, this structure is formulated. So this indicator matrix, as mentioned earlier, it will have each row will be having only one non-zero values. So from that one non-zero value, which column it is that non-zero value is occurring will define that the corresponding row belongs to which graph it is being partitioned, which subgraph it belongs to, so that we can partition based on the first column non-zero values, second column non-zero values, third column non-zero value, and kth non-zero values can be partitioned so that it makes a k partitioning algorithm. So this is the crux of this algorithm. So these are some of the theories being given here, which we don't have time in this. And also they have made some illustrations here for certain uh, problems, which again there are some synthetic problems and also some real world example problems, which we may possibly ask request you to go through that paper. The crux is there are three different way of k partitioning. K is equal to greater than one is like recursively using a k equal to 2 partitioning. Second one is formulating a k eigenvector matrix, and then each row will be considered as a point, and we can use a standard k means algorithm. Third one, as mentioned earlier, we can use the same the crux of the 3.1 and extensible using the indicator form and using the recursive algorithm of 4.1 and 4.2. Thank you. Hope we see something interesting video in the next video. Thank you.